Remember holding a magnifying glass under the sun and watching light ignite paper? That's the magic of concentrated sunlight. But in the real world, when we try to scale this for clean energy, we hit a wall. That's the overall solar to electrical conversion efficiency. Parabolic trough 13 to 15%, power tower 14 to 18%, and parabolic dish Stirling engine systems less than 20%. A staggering 80% is being wasted. What could be the reason for this? Here comes another childhood memory, sliding a finger through a flame without hurting. There's a science behind this. It's the slow rate of heat transfer and time required for that is long. CSP systems reach their optimum theoretical efficiency based on concentration ratio. Efficiency can climb up to 80% at a concentration ratio of 10,000, making it the key limiting factor. Theory promises 80% efficiency, yet large-scale systems deliver under 20%. Why? Photons move at light speed, but heat transfers slowly, so much of the captured energy escapes before use. This inefficiency limits current solar concentration systems and limits our fight against climate change. We've reimagined solar concentration with our dual-stage parabolic concentrator, patented in the US, Europe, India, and China. Uses two perfectly aligned parabolic mirrors facing each other to bounce and refine sunlight into an ultra-thin, ultra-intense, coherent beam. Instead of one quick burst, our system keeps photons engaged longer, delivering their energy gradually into absorber tubes or cavities placed on the rear surfaces of the reflectors, protected by thermal insulation and advanced coatings on the glass covers over the aperture that lock in infrared radiations. The patented system's multiple reflections yield a 5 to 10x concentration boost, approaching thermodynamic limits. Real-world performance depends on ray escape and geometry. The result? Up to 3 times higher photon flux in simulations, and over 30% greater real-world efficiency for a primitive miniature prototype compared to traditional designs. The gap may seem huge, 300% in simulation versus 30% in prototype, but we've identified the causes, and they can be easily corrected in our next lab-scale model. Here are the potential primary use cases for DSPC, to name a few. Utility-scale CSP plants, industrial solar process heat, decentralized thermal systems. At the secondary level, concentrated PV, solar cooling, desalination, solar-based hydrogen generation. At the tertiary level, thermochemical reactors, electromagnetic beam concentration, space-based solar concentration, solar bioreactors, and catalysis platforms. Potential for propulsion systems using concentrated energy for space exploration, and so on. Every deployment replaces fossil fuels, cuts carbon dioxide, and makes industries cleaner and more cost-effective. The global clean energy market is valued at $1.2 trillion today and will surpass $2 trillion by 2030. Concentrated solar power alone is projected to grow 16% annually, reaching $28 billion within a decade. Industrial process heat, desalination, and hydrogen are billion-dollar verticals actively seeking high-temperature, high-efficiency solar solutions, exactly what our patented system delivers. We have the vision, we have the patents, and we have a breakthrough ready to change how the world captures and uses solar energy. Now, we're seeking the right academic research and industrial partners who are ready to lead the charge in a multi-trillion-dollar clean energy revolution. Your mentoring, guidance, and support will fast-track our prototypes, pilot programs, and global rollout, securing your place at the foundation of a world-changing innovation. We would be delighted to hear from you at connect@subalaksha.com. Let's shape the future of energy together.